In this video, we'll be learning how to factor out the greatest common factor for an expression. So before we dive into factoring out the greatest common factor, I just want to talk about the difference between a polynomial that is written in standard form, which you can see over here, where everything is multiplied out. You can see it's written from highest to lowest power, like terms are combined. So this is called standard form, and factored form, where things use factoring strategies to rewrite it so that this, if it was an equation, could be solved. And today we're going to focus specifically on factoring out the greatest common factor, which is going to look something like you see here underlined in blue. And the goal of these is we're going to be finding a greatest common factor and essentially undoing the distributive property on it. So this is what we're going to focus on today. We're going to focus on factoring by factoring out a greatest common factor from an expression. And then these will be focused on in a different video later. So we're going to focus just on greatest common factor today and how we factor expressions using the GCF. So there are two things that we need to keep in mind when we're factoring out the greatest common factor. The first is we are looking for the largest number that both of the numerical components in that expression, or all three, or however many terms you have, that the largest number that they are divisible by. So for example, 12 and 32 can both be divided by 1 evenly, they can be divided by 2 evenly, and they can be divided by 4 evenly. And when we're looking for the greatest common factor, we're looking for the largest number that both 12 and 32 can be divided by. And when we look at those two numbers, the biggest number they can both be divided by is 4. So our greatest common factor here numerically is going to be 4. So we're going to keep that in mind over here. Then we have to look at their variables and see what variables they have in common. And when I look here, I see that the 12 has an x and the 32 has a y, which tells me they don't have any variables in common. So what we're going to do is we're going to essentially undistribute a 4 from each of these. And so we're going to divide each by 4 by factoring a 4 out in front. And when I take 12 divided by 4, I end up with 3, and then the x carries down. And then we're going to take 32 divided by 4, and that's 8, and the y carries down. Now, something we need to keep in mind is whatever we write has to be equivalent. So since we factored a 4 out in front here, the 4 goes out in front to the left. So notice here that all I've done is rewritten this expression in a different way. If I were to redistribute and take 4 times 3x, I would get the 12x. And 4 times 8y, I would get the 32y. So when we're factoring out the greatest common factor, we have to make sure that it's equivalent. So we should have both pieces, both our greatest common factor that we pulled out in front, and then what was left on the inside when we factored that 4 out. Now let's take a look at the second expression over here. So when I take a look at this one, what I notice is that the only number that both 7 and 9 are divisible by is 1, because everything's divisible by 1. So here we can factor out a 1, but just know that everything's divisible by 1, so you can write it or not, it doesn't matter. Then from here, once we find the greatest common number that they're both divisible by, we need to look at our variables. And here I notice that each of these have x's, but they have a different number of x's in each term. So the amount of x's that they have in common is 3, because the 7 term has an x to the 3rd, and this has an x to the 8th. So while there's more x's over here on the right-hand side, it does have at least 3 x's. So we're going to factor out an x to the 3rd. And then when I look at the y's, what I see is that I have a y to the 5th and a y to the 3rd. And so they each, again, have a minimum, or at least, a y to the 3rd. So our greatest common factor here, numerically and with variables, is going to be 1, x to the 3rd, y to the 3rd. And then I need to figure out what's inside of those parentheses. So if I divide 7 by 1, that leaves me with 7 on the inside here. X to the 3rd over x to the 3rd, those cancel out, so the x's are now gone. And then I have y to the 5th over y to the 3rd, which means I have 2 y's, so y squared, left on the inside. And then continue my subtraction, and I do 9 divided by 1, which is 9. I then have an x to the 3rd. X to the 8th over x to the 3rd leaves me with x to the 5th on the inside here, and then the y to the 3rds, because they are equivalent, canceled out. So right here in my box, I have my factored form for this for this expression. Notice if I were to redistribute, it would go right back to where we started, but our goal is to factor out that greatest common factor by undoing the distributive property. So let's take a look at two more examples. So here I notice that I have negative 18 and negative 24. And so when I look at those, there's a lot of terms that they can both divide by. They can both divide by 1, 2, 3, 4, and 6. And I'm looking for the biggest one, so I'm going to factor out a 6 because it's the biggest number that they are both divisible by. So my greatest common factor is going to be 6. Then I need to look at their variables. And so here I have m to the third and m to the eighth. Since the 3 is smaller, I know that the 3 is what they have in common. Now, there are two ways to approach this, so I'm actually going to talk about both here, because with this problem having two negatives involved in it, there are two ways that kids will commonly approach this. So the first way is they'll just factor out a regular 6 out in front. So they'll do 6m to the third, and they'll do negative 18 divided by 6 is a negative 3, and say the m's cancel out. And then they'll do negative 24 divided by 6 is negative 4, and then 8 minus 3 gives us m to the fifth. And so this is one way your answer could be written. However, I do have students that look at this and they say, well, hey, both of those are negatives. So could we instead factor out a negative 6m to the third? And the answer is yes. It doesn't matter which, if you do a positive or a negative, because it expression-wise is going to be an equivalent expression in the simplest factored form. So here if we factor out a negative 6m to the third, we would get negative 18 over negative 6 is 3, and then those m's cancel. Negative 24 over negative 6 is a positive 4, and then 8 minus 3 leaves us with m to the fifth. So you can see here that regardless, we end up with an expression where if we were to redistribute, we would go back to where we started. Now let's take a look at the second example over here. So here we're going to take a look at the fact that we have 3 terms we have to be mindful of. So we're looking for the largest number that 20, 16, and 4 can be divided by. And I know they can all be divided by 1, 2, and 4. And because 4 is the biggest, 4 is going to be what I factor out of those numbers. Then if I look at the variables, I see for x an exponent of 3, 8, and then remember this is a 1 over here. And because x to the first is the smallest, that's all I can factor out that they have in common. And then we have 5, 3, and another 1 for the y's, and so we know I can factor out a 1 for the y's. So let's start factoring 4x to the first, y to the first out. 20 divided by 4 gives me 5. 3 minus 1 leaves me with x squared, and 5 minus 1 leaves me with w to the fourth. And we have minus 16 over 4 is 4. 8 minus 1 gives me x to the seventh, and 3 minus 1 gives me y to the second. Then from here, this is typically the trickiest part for kids. 4 divided by 4 is 1. Notice it's not 0, but 1. It's not gone. And then we have x's cancel out and y's cancel out, so we're left with this expression here. And if I were to redistribute back in, I would go back to this. So factoring out the greatest common factor is all about undoing the distributive property with the largest factor between all of the terms.